Hey there! Have you ever wondered how your computer renders those stunning game graphics, or how AI systems process millions of images in seconds? The secret behind all of that is something called a GPU, a graphics processing unit. Stick around because by the end of this video, you'll totally get what it is and how it works.
Before we dive into GPUs, let's quickly talk about the CPU. The central processing unit. Think of the CPU as the brain of your computer. It's great at handling complex tasks one at a time, super smart, but not very fast when it comes to doing many simple things simultaneously. That's exactly where the GPU steps in.
Here's a great analogy. Imagine the CPU is like a single super fast sports car on a highway. It can do one thing incredibly fast, but the GPU, it's like a massive fleet of hundreds of small buses all moving together at the same time. Sure, each bus is slower than the sports car, but together they can move way more passengers at once. GPUs were originally designed just for one purpose: making video games look amazing. Back in the 1990s, game graphics were getting more complex, and CPUs alone just couldn't keep up with all the math needed to draw thousands of triangles on screen every second. So companies like NVIDIA and AMD created dedicated chips just for graphics, and the GPU was born. So what's actually inside a GPU? At its core, a GPU contains thousands of small processing cores, way more than a CPU. While a modern CPU might have 8 to 32 cores, a high-end GPU can have thousands, sometimes over 10,000 cores. These cores are simpler than CPU cores, but their power comes in numbers. Let's talk about how a GPU actually draws what you see on screen. Your monitor is made of millions of tiny dots called pixels. To display a single frame of a game at 1080p resolution, the GPU needs to calculate the color of over 2 million pixels, and it needs to do this at least 60 times every second. That's over 120 million pixel calculations per second just for a smooth game. Here's something cool. Every 3D object you see in a game or movie is actually made up of thousands of tiny triangles. A character's face, a car, a sword, all triangles stitched together. The GPU's job is to take these triangles, figure out where they appear on your screen, and fill them with the right colors and textures. This process is called rendering. The process a GPU follows to turn 3D objects into a 2D image on your screen is called the rendering pipeline. It goes through several stages. First, the geometry stage, where triangles are positioned in 3D space. Then, the rasterization stage, where triangles are converted into pixels. And finally, the shading stage, where each pixel gets its final color, shadows, and lighting. Inside the rendering pipeline, there's a key concept called shaders. Shaders are small programs that run on the GPU cores to decide how every pixel should look. There are vertex shaders that handle the shape and position of objects, and pixel shaders, also called fragment shaders, that handle the color, texture, shadows, and lighting effects for every pixel. Just like your CPU uses RAM to store data it's working with, the GPU has its own dedicated memory, called VRAM, video RAM. This is where the GPU stores textures, frame buffers, and all the data it needs for rendering. The more VRAM you have, the higher resolution textures and more complex scenes your GPU can handle without slowing down. The true superpower of a GPU is parallel processing. Think about it like this. If you need to paint a huge wall, one painter working alone would take forever. But if you have 5,000 painters all painting different sections at the same time, you're done in minutes. GPU cores work the same way. They split a massive task into thousands of tiny pieces and tackle all of them simultaneously. So, should GPUs replace CPUs? Not at all. They each have their strengths. CPUs excel at sequential tasks, things that require logic, decision-making, and running operating systems or programs step by step. GPUs shine at tasks that can be broken into thousands of identical parallel calculations, like graphics rendering, physics simulation, or training AI models. Let's talk real-world use cases. In gaming, the GPU is responsible for everything you see. The detailed character models, the realistic lighting, the reflections on water, the explosions, the shadows. Modern games use advanced techniques like ray tracing, where the GPU simulates actual light rays bouncing off surfaces, creating incredibly realistic visuals. Beyond gaming, GPUs have become the backbone of artificial intelligence. Training an AI model means doing billions of small math operations, multiplying numbers in matrices over and over again. This is exactly what GPU parallel cores are perfect for. Companies like OpenAI, Google, and Meta use thousands of GPUs together to train large language models like the ones that power ChatGPT. GPUs are also essential for video editing and content creation. When you export a 4K video in a program like Adobe Premiere or DaVinci Resolve, the GPU accelerates the encoding process, cutting export times from hours to minutes. Even video effects, color grading, and transitions are processed on the GPU to give you real-time previews. There are two types of GPUs you should know about. Integrated GPUs are built right into the CPU chip. They share system memory and are great for everyday tasks like watching videos or working on documents. Dedicated GPUs are separate, more powerful chips with their own VRAM, perfect for gaming, video editing, and AI work. When it comes to graphics cards, two names dominate the market. NVIDIA's GeForce RTX series is famous for ray tracing and AI-powered features like DLSS. AMD's Radeon RX series offers great price-to-performance ratios. Intel has also entered the market with its Arc series. Each brand has its strengths depending on your budget and use case. So, how does a GPU actually connect to your computer? Most dedicated GPUs plug into a slot on your motherboard called the PCIe slot, short for PCI Express. Data moves between the CPU, RAM, and GPU through this high-speed connection. The GPU then outputs the final image to your monitor through connectors like HDMI or DisplayPort. The future of GPUs is incredibly exciting. They're no longer just for gamers. AI accelerators, neural processing, real-time ray tracing at 8K, and even running large language models locally are all pushing GPU technology forward at a rapid pace. With trends like cloud gaming and AI-generated graphics, GPUs are becoming the most important chips of the modern era. Alright, let's do a quick recap. A GPU is a specialized chip designed to handle massive parallel computation. It was born for gaming graphics, but now powers AI, video editing, science, and more. Its thousands of cores work together simultaneously, unlike the CPU, which handles tasks sequentially. Whether you're gaming, creating content, or training an AI model, there's a GPU working hard behind the scenes. I hope this cleared things up for you. If you found this helpful, hit that subscribe button, and I'll see you in the next one. Cheers!